So I want to thank the organizers for the opportunity to speak at this meeting. I've heard about Wavefront Congress for years and have been really impressed by a lot of the innovations that have been shared at this meeting. And the objective of my talk today is to share with you some of the innovations that have been developed over the past 5 years or so that take us beyond just imaging what adaptive optics is famous for, and imaging photoreceptors in the back of the eye, to new cell types which have the potential to shed light on retinal disease in the eye. So the title of the talk, Beyond Photoreceptors, Using Adaptive Optics to Image the Behavior of Blood Cells. And the focus of my research group is to use adaptive optics technology as a tool to investigate the vascular perfusion of our eye. Many of you are familiar at Wavefront Congress of the utility of adaptive optics imaging to measure and correct for the aberrations of the front of the eye. And I think the hallmark images that come to mind when we think about adaptive optics are some of the stunning images that have been produced of photoreceptors. So clearly there's been a long lineage and progression of this from the earliest work by Liang, Williams, and Miller, which showed in a flood instrument the ability to image the cone photoreceptors. Further improvements still with adding densitometry, which allowed to do cone classification, as shown by Roeder and Williams. And further improvements in the late 2010s by Duber and colleagues, which really pushed the envelope of the diffraction limited capabilities of AO, which allowed them to see not only cone photoreceptors, but also rod photoreceptors in between, which are even smaller, and really pushing the limits of what adaptive optics can see in terms of resolution. But the focus of today's talk is not going to be so much on photoreceptor cells, but on other cell types that we can image in the back of the eye. And as a disclaimer, or to cover most of the talk, the data that I'll show in today's talk comes from this animal. This is a laboratory mouse. And here at the University of Rochester, we have several instruments that are developed for imaging this very tiny eye. So the pupil of the mouse eye is around 2 millimeters in diameter, quite a bit smaller than what you get in a human, but it provides a number of optical advantages, including a very large numerical aperture, which actually provides enhancements in the cells that we can image inside the living eye. So the data I'll be sharing today come from this little animal. And so when you think about the cross-section of the back of the eye, this is a very thin sheet of neural tissue, slightly thicker than, really a thick piece of paper. In the late, and about 10 years ago, the capabilities of adaptive optics scanning light ophthalmoscopes in confocal mode, this is using the confocal principle to make illumination light and confocal detection at the same conjugate plane, really excelled at imaging, to be honest, a fair limited number of structures at high resolution in the back of the eye. Things that could be imaged with this modality were, of course, photoreceptors, the capillaries, which are quite tiny in the back of the eye, really microscopic, about 1/10 the thickness of the human hair, and of course the nerve fiber bundles that backscatter light very effectively. These structures are fantastic to image in the conditions of health and disease, but as you see from this cartoon, there's still a lot of neural and glial cells that we'd like to image. And of course, the challenge is that most of the neural retina is translucent or transparent, making these cells really difficult to image. So over just the past 5 years or so, our group and a number of others using AO technology have developed a class of technologies which are sort of grouped together as called phase contrast. This goes by a number of different names: split detection, offset aperture imaging, multi-offset aperture imaging, and others. But basically, the operating principles are similar in that we're capturing non-confocal light in order to optimize the multiply scattered and refracted light at the level of single cells in the back of the eye. And this modality has really undergone dramatic changes in the number of cells that we can visualize inside the living eye. In this case, in the mouse, ganglion cells, blood cells, horizontal cells, photoreceptor somas, and of course, the distal processes of photoreceptors. Because our tool is used in the mouse, we also have the additional advantage that we can combine with confocal imaging the addition of fluorophores. And using the vast transgenic library you see in a mouse, we can image things like ganglion cells, microglia, pericytes, and basically any cell that has a unique protein that can be sparsely labeled in the retina could be imaged with fluorescence modalities. But the bulk of today's talk is going to focus on these cells. And I love showing this image because it reminds us all that the blood that's flowing through our body is not just this fluid, but it's in fact particulate in nature. In a human, we have about 35 trillion, that's trillion with the T, of these cells that are circulating throughout our entire human body. And with it, it contains tremendous information, not only about the health of the eye, but also holds with it the potential to image systemic disease as well. So here is a familiar scanning electron micrograph of a red blood cell, pseudocolored in red, a white blood cell in blue, and an activated platelet. This is, of course, an image that's taken outside of the body. But we are very interested in understanding the anatomy, morphology, and behavior of these cells inside the living eye. And this will be the focus of today's talk. As mentioned before, we're imaging the mouse. And those of you who have not gotten a very close glimpse of your house mouse, this is what our preparation looks like. Just to illustrate very quickly, the animal is asleep. He is breathing anesthesia. This is isoflurane gas. And we usually have about 2 hours of recording time. Mydriatics and cycloplegics are applied to get that full, nice, beautiful round pupil. And we actually apply a very tiny custom-made contact lens to keep the eye hydration intact over time. With this preparation, this is an image taken with the commercial Heidelberg HRA. We can see that we have a very stable preparation where we can get this 2 hours of recording and get very beautiful images of the vascular perfusion in the back of the eye. This is, of course, without adaptive optics. What we'd like to be able to see really the cellular level detail with AO capabilities. And so today I'll be sharing with you three new capabilities in the field over the past 5 years that really have allowed us to study blood cells inside the living eye in new ways. The first will focus on the tiniest of capillaries. These are capillaries that are about 1/10 the thickness of a human hair, about 3 to 4 microns in luminal diameter. Not only imaging those capillaries, but the blood cells within that capillary network. Turning the adaptive optics camera now to the biggest of vessels, we can also certainly see those big vessels without AO, but AO allows us to see the individual blood cells, providing detailed measurements of the velocity of hundreds of thousands of cells per second. And the balance of today's talk will focus on the inflammatory response in the retina. This is something that happens in almost every retinal degenerative disease, is there's an inflammatory component, and we're seeing some of the first glimpses of this using AO technology. So let's start with the capillaries. About 10 years ago, this is where the state of the art was in AO imaging. Here's a stabilized field visualizing the capillaries, which are about 3 to 5 microns in diameter. And combining AO with video rate mode, you can certainly see the movement or twinkle of those erythrocytes as they're moving through the capillary network. But in the past few years, we've combined with this technology phase contrast imaging. I'll not spend a lot of time in describing the mechanisms, but if any of you are interested, there's a recent publication on this which describes one optical model, which may describe how the phase contrast is generated through the optical principles of light refraction at the level of single cells in the eye. Hopefully, I can convince you the image at right is slightly better in that we can actually see the morphology and deformation of those blood cells. And of course, that's very important to understand vascular-associated disease in the eye. Also highlight your attention here to this capillary, which is never perfused with blood cells, which is really quite interesting in the conditions of health and disease of the eye. And we can also see capillaries that occasionally stop perfusion and then reperfuse. We're particularly interested in these events in vascular-associated disease of the eye because it's long been posited that these early sentinel events of stoppages of blood flow may combine to wreak havoc on vision as the neurons and glia require a constant blood supply in order to maintain health. But of course, we want to improve adaptive optics further to get greater images of these blood cells. And so I've demonstrated that we have adaptive optics, which provides us very good resolution. We've combined with that phase contrast, which provides now optical contrast in weakly backscattering or translucent cells. And the third component that we could really improve is temporal resolution. Of course, these moving blood cells are moving incredibly quickly. And so the strategy that we've employed has been borrowed from a very elegant strategy provided by Steve Burns at Indiana University. And it is as follows. Instead of scanning the entire image that you would in a typical raster system, we're instead now just performing a very fast line scan across a single vessel of interest. And when you do this and scan, in the case of our resonance scanner, about 30,000 scans per second, what you image is the self-scanning of the blood cells as they pass by the stationary beam. And what you have here is a literal ticker tape of the passage, morphology, anatomy, and counts of every single blood cell that passes by this beam. This provides the greatest level of detail that we've ever seen in terms of vascular perfusion, now enabled with adaptive optics plus these modalities. One of the first things that we wanted to examine looking at the anatomy of these cells is that many technologies like OCTA, OCT angiography, are very good at telling us whether or not vessels are perfused. But for example, you would lose the appreciation of the morphology of the packing of blood cells within those capillaries. So what I'm showing you here are a number of capillaries imaged in the same mouse from the same capillary network that have capillaries of almost equivalent diameter. The diameter of these capillaries are about 3 to 4 microns in diameter. But despite having similar perfusion and being connected to the same heart, the density and packing of these blood cells is really dramatically different. For example, the packing of blood cells often shows sparse and dense configurations, different velocities, interdigitations, which show zigzag interdigitations of these cells, disordered blood flow, and interrupted, which we'll talk about in just a second. But the panel that you see at right shows us that we can actually image the motion of these blood cells and that the packing density actually conforms to mathematical models which simulate the lowest energy state of the packing of these erythrocytes inside the vascular system. So let's return back to that interrupted flow that we see at the bottom. It's very difficult to interpret what's going on in that image. This is now coming back to raster scanning, what an interrupted flow looks like. The video at left is a 10-fold speed up of what it is that we can see with phase contrast plus adaptive optics. This is the formation and resolution of a clot or a little thrombus within these tiniest of vessels. And the question is often asked of us, are these red blood cells? Are they white blood cells? Are they activated platelets? The image at right, you can actually now see and discern that these guys are red blood cells. And then you see the passage of this slow and sticky lethargic cell, which is moving through, which is not now biconcave, but biconvex, indicating that it's in fact a sticky white blood cell. This is of high importance for clinical medicine because it's long been thought that sticky white blood cells are the cause of vascular non-perfusion, especially in conditions like diabetes, in which there is an inflammatory component. We'll get back to inflammation in just a minute. There won't be a lot of time today to talk about measuring velocity in the biggest of vessels, but I did want to mention very briefly that we've built a tool set that not only can now scan across the smallest of vessels, but can scan across the biggest vessels in the same fashion, and now developed an automated pipeline that can measure the velocity of hundreds of thousands of cells per second. Paper forthcoming is now looking at real-time measurements of this, which would really ramp up the utility of this in the clinical setting. But I think because we're limited on time, I'm going to spend most of the balance of today's talk on this very exciting finding over the past couple of years in my group, that not only can we study blood cells within the vessels, which is where they belong in a healthy retina, but also image those blood cells when they escape. These are not necessarily leaks, but purposeful movements of the immune cells as they leave the microvascular system in response to inflammation. How do we do this? We have mice. These mice are healthy adult mice. We image their retinas with adaptive optics. This is a venule very close to the optic disc, and you can also see passing nerve fiber bundles and the capillaries at this plane. Now, because the imaging is non-destructive, we can come back and visit the same area, but now visit the same area after we induce inflammation in the eye. And the way that we do this is we inject an irritant into the vitreous humor. This irritates the retina. It's called LPS, lipopolysaccharide, and it's a very strong inflammatory cue in any tissue. What we see when we return back to this tissue just 72 hours after this inflammatory event is nothing short of remarkable. We can see the dramatic arrival of immune cells into this neural tissue. The slides that follow will hopefully convince you that these are in fact neural cells and not, for example, inflamed glia or neurons in the retina. How do we know that they're immune cells? Well, this is where time-lapse videography really helps us. The movement of immune cells are actually moving quite slow, glacial, in fact, micrometers per minute, and often is the case. So when we combine AO plus phase contrast plus detailed images over hours, again, with the benefit of patient subjects and mice, we can now image the dramatic behavior of moving and purposeful behavior of immune cells. And I love showing this image because every single cell can tell its own unique story. And you can really stare at these images for hours on end and try to understand what's going on in the retina. But for today's talk, I'm going to illustrate just two examples. The first example, I want you to pay attention to this red circle. And if you pay attention to this red circle, you'll see a single immune cell right now leaving the vessel. To our understanding, this is the first time that this has ever been seen inside a living eye. This is called extravasation. And in the retina, this is a very important event, which is the point at which an immune cell leaves the vascular system and enters the neural parenchyma. The other example that I'd like to show you is in this green circle. And this might not seem remarkable, but this is really quite controversial in the field of immunology. What you see here is an immune cell that is outside the vessel come back inside the vessel. This is called vessel reentry and has been seen in very few tissues. In fact, many immunobiologists don't believe that this can happen. But this, if true, if found in the retina, would really revolutionize our understanding of how the immune response builds adaptive immunity inside the living body. Again, another opportunity to understand science and clinical medicine through the advent of adaptive optics. Of course, the device is non-invasive, which allows us to return to the same tissue. Here's a healthy retina. We inflame the retina by the injection of this lipopolysaccharide into the vitreal humor. And now we can come back to that same tissue 6 hours later, and you can see the dramatic changes in the appearance of the retinal tissue. If you pay attention to this venule right here, you can actually see the rolling behavior of leukocytes. This is one of the first steps that slow the immune cells down before they extravasate into the tissue. But even 6 hours later, you can see the arrival and movement of those immune cells in the tissue. Now, 24 hours later.
Just say, sorry, just 30 seconds.
30 seconds. I'm on the last slide, Gunyong.
Yeah, great.
The single immune cells, as they move within the neural retina and then return to this tissue 72 hours, 10 days, and 2 months later. This inflammatory response has escalated and then resolved. And this is what clinicians dream of. We're hoping to port this into human imaging soon. So just to summarize the talk, we have three brand new capabilities: being able to image tiniest of capillaries, being able to image the biggest of vessels and measure blood speed there, and then also finally imaging the immune response inside the living eye. This is the team that does the very exciting work, and thanks to our funding sources for making this possible.